Welcome back to Power Series on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. Alright, here's our third example of using a power series to determine the interval of convergence. Alright, so let's look at our series here. We've got the series from n equals 1 to infinity of 2 to the n power over n, and then times the quantity 4x minus 8 raised to the n power. And remember, we start off by using either the root test or the ratio test to determine the limit L. In this case, it looks like the ratio test will be much easier to use, so we'll use the ratio test. So our limit L, we know from the ratio test, is the limit as n goes to infinity. And we're going to start off with all of our n plus 1 terms. So anywhere I see an n, I'll have an n plus 1. So 2 to the n plus 1 times 4x minus 8 raised to the n plus 1 power divided by n plus 1. And then I essentially just multiply by the reciprocal of the argument of the power series. So times n divided by 2 to the n divided by the quantity 4x minus 8 to the n power. All right, and remember, ratio test has absolute value signs. We know that's important for our future step. This is equal to the limit as n goes to infinity of, and what I can do is each n plus 1 term, I can simplify that as a product. So 2 to the n plus 1 is 2 times 2 to the n, right, by exponent laws. The 4x minus 8 term becomes 4x minus 8 to the n power times just a 4x minus 8 to the first power. And the n plus 1, I really can't do anything with that in the denominator. But notice what's going to happen is a lot of stuff is going to cancel. For example, the 2 to the n is going to cancel because it's on both sides. The 4x minus 8 to the n power cancels. And so I'm left with the limit as n goes to infinity of 2 times the quantity 4x minus 8 times n over n plus 1. All right, what can I do here? Remember that the x terms, this one is only in terms of x, it has no n in it. And since the limit is only in terms of n, I can pull the 4x minus 8 outside the limit. But remember, since I have these absolute value signs, I have to keep the absolute value signs around the 4x minus 8 when I pull it out in front of the limit. So therefore, all this, the limit is equal to the absolute value of 4x minus 8 times the limit as n goes to infinity of 2n over n plus 1. And again, absolute value in here, but it's not really as important there. Really, the limit part as n goes to infinity of 2n over n plus 1, you can evaluate this with any method you want. It should be pretty obvious either by the exponent rule for evaluating these or L'Hopital's rule that the limit is just 2. All right, so the limit is the absolute value of 4x minus 8 times 2, and I can throw the 2 out in front of here. So 2 times the absolute value of 4x minus 8. And now that I've actually determined what the limit is, I set it less than 1, because L has to be less than 1. So, down here, I've rewritten it. 2 times the absolute value of 4x minus 8 has to be less than 1. Now what I'm going to do is divide through both sides by 2 to get rid of that coefficient. So, the absolute value of 4x minus 8 is less than 1/2. Alright, so I got fractions in this one, unfortunately. Now, remember, I have an absolute value sign here, so I have two cases, one endpoint for each case. All right. In the first one, I'm going to have 4x minus 8 is less than 1/2, basically just as it's written minus the absolute value signs. But in the other case, remember what I have to do is flip the sign of the inequality and change the 1/2 to being negative. So the second case will be 4x minus 8 is greater than negative 1/2. That's going to give me my second endpoint. All right, let's evaluate each of these cases. All right, so 4x minus 8 is less than 1/2. Let's add 8 to the other side, which is the same as 16/2. So 16/2 plus 1/2, that means 4x is less than 17/2. And if I divide through both sides by 4, I have x being less than 17 over 8. All right, that's my first endpoint, or at least one of them. Let's look at the second case. So if I have 4x minus 8 is greater than negative 1/2, let's add 8 to the other side, or add 16/2. 16/2 plus a negative 1/2 is the same as 15/2. So therefore 4x is greater than 15/2, and dividing through both sides by 4, I get that x is greater than 15 over 8. So therefore, if I combine these two separate inequalities into a combined one, it says that my rough interval of convergence is between 15 over 8, and 17 over 8 for x. In other words, if I plugged in, let's say, 16 over 8, so that's definitely in the middle. If I plugged in 16 over 8 into this value of x in the power series we would converge. Outside of this interval, we definitely know that the power series would diverge if we plug in those values of x. So we know our endpoints, 17 over 8 and 15 over 8, but we don't know if on these points the power series converges or diverges, so we need to check the endpoints. And that's what we're going to do on this slide. All right, so this is what we just did, where we set L less than 1. So we have our two endpoints, 15 over 8 and 17 over 8. Let's go ahead and check those endpoints. Let's do the lower endpoint first, doesn't matter. So if I plug in 15 over 8, I have the series from n equals 1 to infinity of 2 to the n over n times 4 times 15 over 8 minus 8, since we had 4x minus 8. If you simplify all of this inside the parentheses, raised to the n power, it becomes negative 1/2 to the n power. Okay? And what you can further do with this seemingly alternating component, this negative 1/2 to the n, is you can break it up because it's a quotient, all raised to the n power. So I still have series from n equals 1 to infinity of 2 to the n over n, but I can take the numerator and make it negative 1 to the n, and take the denominator and then times 1 over 2 to the n. And again, remember with most of these problems, they're designed to work out nicely. The 2 to the n's cancel here. Okay, and all I'm left with is the series from n equals 1 to infinity of negative 1 to the n power times 1 over n. Now, if we were lacking this alternating term and just had 1 over n, that would actually be the harmonic series. But when we have this 1 over n and then times a negative 1 to the n power with an alternating term, that's called the alternating harmonic series. And depending on how rigorous your professor is, they may ask you to show that this alternating series converges. But you could, in some cases, you might be able to just memorize, and it might be sufficient to say that it's a known fact that the alternating harmonic series converges. So, in other words, 15 over 8, if we were to plug that x value into the original power series, the power series would converge on x equals 15 over 8. Therefore, 15 over 8, since that endpoint converges, this endpoint is included in the final answer. So if we were to express this inequality correctly, so far at least, we'd need to put in a little line under this less than sign, because 15 over 8 is included. That will cause the power series to converge. All right, now for the second endpoint, 17 over 8, let's do the same thing. So if we plug that in for x, we have the series from n equals 1 to infinity of 2 to the n power over n times the quantity 4 times 17 over 8 minus 8 raised to the n power. Not surprisingly, all this in the parentheses adds up to be 1/2 raised to the n power, and we can play the same game from before. We can break this up. 1 to the n power, that doesn't do anything, that's just 1. But this denominator, 2 to the n power, we get a 2 to the n power down here. So our series becomes, from n equals 1 to infinity, of 2 to the n over n times 1 over 2 to the n. And clearly the 2 to the n's cancel here, and so the final series is n equals 1 to infinity of 1 over n, which we know that as the harmonic series. That's our regular harmonic series, and we know that that diverges. So 17 over 8, that x value, will cause the original power series to diverge. Therefore, 17 over 8 cannot be included in the interval of convergence. So, if we express it in this way, only the 15 over 8's inequality sign will have the line under it, but the 17 over 8's will not. Or we can write it in this notation, where the interval goes from 15 over 8 to 17 over 8, but it includes the value 15 over 8. Therefore, we have this bracket over here, and the parentheses over here indicates that the 17 over 8 is not included. All right? And for the radius here, I actually have a little mistake there. Let me actually go in here to fix that. So the radius should actually be 1/8. And how do you determine the radius of convergence given the interval? Well, what you can do is you can actually take the upper limit minus the lower limit. So 17 over 8 minus 15 over 8 is 2 over 8. And then just divide that by 2, and you get 1 over 8. So if you take the upper limit minus the lower limit, divide it by 2, that's your radius of convergence, okay? And it makes sense because a radius is half a diameter in terms of a circle, I suppose. All right, so Hopefully this video gave you a little bit of intuition and understanding, more so for power series and finding the interval of convergence. In the next few videos, what we're actually going to do is talk about power series representations for functions, and we're actually going to find a few separate ways that we can actually do that. Alright, so please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.